So last class, we were talking about bell curves. And in particular now, we're talking about situations where we use bell curves. Last class when we introduced bell curves, that was the first situation we used bell curves, which is we're given or told that that variable is distributed as a bell curve. So given that the variable is normally distributed, so normally distributed is just another word for distributed in the shape of the bell curve. So as a review, if the question had been weights of men are normally distributed, and you're told to mean the standard deviation with mean 180 and standard deviation 20. So here you're flat out told that this variable of interest, which is weights of men, is distributed in the shape of a bell curve. You're also told the mean, you're told the standard deviation. And you're asked to find the probability that a man's weight is greater than 200 pounds, let's say. Then as a review, how would we go about answering this question? Okay, very good. So find the z-score, but let me back up half a step. Let's go ahead and draw a picture first. So because we know that this variable is distributed as a bell curve, you can go ahead and draw out the shape of the bell curve for this variable that represents the weight of a man. And we can go ahead and identify this reference point of 200 pounds. Let's say 200 is here, because we know that 180 is the mean or the peak of the bell curve, and 200 is more than that. And so we're trying to find the probability that this variable that is in the shape of this bell curve, and we're told that, is greater than this reference number of 200. And so the probability of being greater than is the same as the area to the right of that number under the bell curve. So this probability will be the same as finding the area to the right under the bell curve of that number.
Wouldn't we technically already know it since it's only one standard distribution away, and we just have to switch that?
Yeah, very good. So we're just going through the general procedure that would work for any finding any probability of a bell curve situation. And like you said, we might be able to simplify easily, but these are the general steps. So now we're gonna go ahead and find this right area, and the first step to do that is find the z-score. So we need to find the z-score of this data point of 200. And remember, the z-score of the data point is the number of standard deviations that this data point is away from the mean. So this data point is 20 pounds away from the mean, but there's 20 pounds in each one standard deviation. So how many standard deviations are we away from the mean?
One.
Or one. So the z-score turns out to be exactly one. So either you could have realized that, or even if you calculated it in general, you would also have come up with that. So in general, it would be this data point minus 180 divided by 20. And that's where we're getting the 1, and the 1 represents this data point being one standard deviation away from the mean. Okay, so as review, what's the next step? After we get the z-score, how do we go about finding this right area? Yeah, good. So we're gonna go to the z-score table. That gives us a relationship between z-score and area to the left of that z-score under the bell curve. So we're gonna look up a z-score of exactly 1 and see what left area we get.
It'll be, 8413.
Okay, good. 0.8413. So this left area is 0.8413. Oops. But this is the left area, so remember the table always gives us the area to the left of that z-score that we're looking for. But we want the area to the right under the bell curve, so how do we find that? Yeah, we subtract from 1 because we said that the total area under the bell curve adds up to 1. So this will end up being 1 minus 0.8413. So we're gonna get 0.1587. So that's the right area we're looking for. And so that right area will be the same as the probability that this variable representing a man's weight is more than this number of 200 pounds. So this means that 15.87% of all men will weigh more than this random man that we just selected. Any questions? So that's review. And the point is that this is the first instance where we use bell curves in that we're told that this variable was normally distributed, and we can't assume that it's a bell curve. We're told explicitly that it's a bell curve. Okay, so the next instance we use bell curves comes from the central limit theorem. And we started talking about this last class. And we said that the central limit theorem was I'll abbreviate central limit theorem as CLT. Sounds like a sandwich.
Chicken, lettuce, and tomato.
Yep. So this chicken, lettuce, tomato theorem, what it says is that the distribution of sample means, right now we have the distribution of individual values, the distribution of the weights of a single man. This is what distribution we currently have originally. But the central limit theorem says that the distribution of sample means, if we were to collect different samples from this original population of weights of men, then the distribution of the sample means, so if we collect a bunch of samples and then we find the means of each of those samples, the distribution of those sample means.
Alert. Appropriate directions would have followed. Thank you and have a great day. This is a test of the EFSC emergency notification system. This is only a test. This is a test of the EFSC emergency notification system. If this had been an actual emergency situation alert, appropriate directions would have followed. Thank you and have a great day. This is a test.
Wow. Okay. So what the central limit theorem says is that the distribution of sample means, and what that means is that if you look at your original distribution, the original distribution is the distribution of individual values. Here, individual weights of a man. But if you were to collect samples from this original distribution and find the means of each of those samples and keep doing that, then if you were to find the distribution of those sample means, then that distribution will end up being a bell curve, which is normally distributed. And not only do we know that that resulting distribution of sample means is a bell curve, we know what the mean and standard deviation are. So the mean, so with a mean that is equal to the original population mean of individual values, but the standard deviation will be different. The standard deviation will be the original standard deviation divided by the square root of the sample size. And we said that this will end up being true. Well, the resulting distribution of sample means will indeed be a bell curve. It will be true if the sample size n is at least 30. So either that could be true, or if that's not true, then the original population of individual values is already distributed as a bell curve. Or original distribution of individual values already normally distributed. I'll say already bell curve. Okay, so this is what we talked about last time. This is very abstract, but let's make it concrete with an example now. So let's say that we take this distribution of weights of men that has this mean of 180 and the standard deviation of 20. And let's say that we select a sample of 100 men. And then when we have 100 men, we weigh each of the 100 men, and then we punch in the weights of those 100 men into our calculator, and the calculator will give us the mean and standard deviation of the weights of those 100 men. So let's say that the mean of this sample ends up being, well, let's just know for now that the calculator will give you some mean and some standard deviation, but the actual values aren't important, so I'm not going to write them down. So the important thing is that the sample mean weight of those 100 men is found. So the question is, what's the probability that that sample mean weight for the 100 men is greater than 200 pounds? So this looks like a very similar question to the one that was just solved for. But the previous question was, what's the probability that a single man's weight weighs more than 200 pounds? And all we did was, because we were told that a single man's weight is distributed as a bell curve with a known mean and standard deviation, we just found the z-score and looked at it from the table to find that probability. And then the answer we got was about 15.87%. But the answer to this question, do you expect it to be the same as before, or if not, less than or greater than? Okay, so a vote for less than. Same, okay. Anybody for greater than? All right, why are you saying less than? Sure.
There's just a gut instinct.
Okay, that's good, that's good. So it's also, so you notice that in this class, students often ask, how do we know when to use an equation? And often that comes from building up intuition as we go. And part of this is I'm trying to develop your intuition by asking you what you should expect. And so training your intuition and your instinct are just as important. And so before we actually talk about cranking out the numbers, let's focus on developing intuition and instinct here. So, again, those of you who haven't answered yet, do you think this answer should be less than, equal to, or greater than the previous answer that we had found before?
I'm guessing it's gonna be less than.
Okay,
Because,
I see.
a sample mean is different from just any specific man. The sample mean would be closer to 200, so I mean greater than. Yeah, it'll be greater than
Are we greater than?
the
Okay.
probability of the man's weight.
So why do you say greater than?
Because, any man's weight, there's more of a chance for it to be less than 200 pounds. For specifically the sample mean weight, there's a specific number that we have in mind, and so there's a greater chance of it, especially considering that 180 was the, well, we don't know the sample mean, so, but I'm
Okay,
guessing that
okay.
it would be greater than.
So if you're selecting a random man, that means 15% of the time, his weight will be greater than 200 pounds. But if you take 100 people's weights and you take the average, you think that that average will be greater than 200 pounds more than 15% of the time, like 20% of the time, 30% of the time. What the rest of you guys think?
Less than.
Less than, why is that?
The exact opposite of what you just said, basically.
Okay.
So your sample size is 100, so you're basing it off 100 people, but if the selected one of just a normal distribution is 15% greater than 100, then well, what is that basically based off of?
What is what based on?
Problem one.
It's based on this mean and standard deviation that are given to you, assuming that these are true, and these are realistic numbers. So, meaning that the average of all men's weights is
So all men,
180
you're
pounds.
saying all men.
All men.
So yeah, so that'd be all. So you're saying 100 men, so out of 100 men it'd be less, because you're not going after all of them. You're going after a select. Actually, wouldn't it be the same?
Okay, okay.
I don't know.
So very good. So this is very important to think about this first before we just chug out the numbers. Yeah.
I feel like it will also be the same, because wouldn't you just multiply 100 by your
Yeah.
probability, and then that's the same number as before?
Okay. So even though we're saying that this mean is out of all the men, it's basically each person's individual weight out of all the men. So what we're saying is that if you were to weigh each man, like each of the hundreds of millions of men in the country, and you were to weigh them, now you build a histogram and you look at a certain person's weight, like 180 pounds, and then you count the number of men in the whole country that have that weight. And then that's the height of your bar. And so that's why this probability distribution would end up looking like this bell curve. And then if you took each of those weights out of the hundred millions of men and then added them all up and divided by the total number, that would be the 180. And the standard deviation is 20.
Yeah.
Okay, but what this is saying is if we took the sample mean weight for the 100 men, which means that now you have 100 men's weights all distributed this way, right? Where the mean of those 100 is also going to be 180, and the standard deviation of those 100 will also be 20. However, for each of those values, we're going to find the mean of that. So let's say that one time you gather a sample of 100 people, and the mean ends up being 180. Another time, and this represents out of a sample of 100. So this is in sample of 100. The sample mean turns out to be 180. In another sample of 100, so second sample of 100, let's say the sample mean ends up being 182. So now you notice that these sample means are pretty close together. You don't have the same amount of variation that you did in the original distribution of individual values. Because when you take the mean, you're gonna have the smoothing effect, where now the sample means will be close together. And so maybe the third sample of 100, the sample mean will now be, let's say, 179. So they're all clustered around this original mean of 180. So now, the question is, this probability that the sample mean, so now you take the, each of these sample means, what's the probability that any of these will be greater than 200? So do you think the likelihood will be less than or more than before?
Less than.
Yeah, because of the fact that these sample means will be clustered around this mean of 180. So it has a lesser chance of being spread out and to hit this 200. So that's one way to think about it. So you would expect this probability to be actually much less.
Can you actually solve it with just that amount of information?
Yeah, so we can solve it using this new idea that we talked about called the central limit theorem.
Okay.
So we're gonna solve it, but right now we're just talking about the intuition. So a second facet of this, to aid the intuition, is to think of it this way, as if we have, let's say we have 10 numbers, and we want, let's say 5 numbers. We have 5 numbers and we want the mean of the 5 numbers to be greater than 10. So if we want the mean of the 5 numbers to be greater than 10, what do you think should be true about each of the numbers individually? Or collectively?
Most of them should be greater than 10.
Yeah, very good. So if you want the average of 5 numbers to be greater than 10, each of the numbers in particular should be greater than 10, or at least most of them should be greater than 10. So if you have one number that's only 1, for example, there needs to be another number that makes up for it by a lot, right? The other number needs to be 11, for example. And if it's not, then you don't have a way for the mean of all the numbers to be greater than 10. So same thing here, if you want the mean weight of 100 men to be greater than 200, then most of them have to have a weight that is greater than 200. So now you're putting a much greater restriction or a much greater constraint on what the numbers need to be. So here you're requiring most of the 100 numbers to all be greater than 200, versus before, in the previous question, you're only requiring one man to be greater than 200 pounds. So that's a big difference too. So in the previous question, you're requiring one man to be more than 200 pounds. Here you're requiring the average of 100 men to be more than 200 pounds. So most of the 100 men all have to be greater than 200 pounds. Any questions? All right, so now let's go ahead and use this idea of the central limit theorem to actually quantify this and get the number for this. So previously, the way that we approached this situation was basically to find this probability. We looked at the distribution of this variable, and then we drew out the picture. And previously, this variable was just the weight of a single man. But in the previous question, we were told the weight of a single man was normally distributed. That's why you could go ahead and draw out the bell curve. And we were also told exactly what the mean and standard deviation was for that bell curve. But in this case, for this variable that represents a sample mean weight, we're going to use this idea of the central limit theorem that tells us that the distribution of sample means is normally distributed. And it tells us that the mean and standard deviation of this new distribution is as follows. So we're going to go ahead and draw out this new bell curve with this new mean and this new standard deviation. So I'm going to draw out the distribution of this variable, which represents the sample mean weight. But now this bell curve, even though it's a bell curve like before, it's a bell curve with different parameters. Different mean possibly and a different standard deviation. So the mean and standard deviation of this bell curve will come from that central limit theorem. So what does the central limit theorem tell us that the new mean is?
20.
Yeah, it tells us that it's equal to the original mean. And the original mean of the distribution is 180 pounds. But what does the central limit theorem tell us that the standard deviation is?
Standard deviation divided by, I forgot the word.
Yeah, it's gonna be the original standard deviation divided by the square root of the sample size. So, the square root of the sample size which is, the original standard deviation is 20 divided by the square root of 100, or 10. So that ends up being 20 divided by 10, which is 2, so the standard deviation is 2. So now that we have this new bell curve, the probability we're trying to find, the approach is the same. So we're trying to find the probability that this variable is greater than this reference number. So now that we have the distribution of this variable, we're gonna label this reference number. And because we're trying to find the probability that the variable is greater than the reference number, that's the same as finding the area to the right of that number under the distribution. So just like before, we're trying to find this area, but with this new bell curve with these different parameters. But the approach is the same, in that the next step is to find the z-score, and then we're gonna look the z-score up under the table to find the left area, and then subtract from 1 to get the right area. So let's go ahead and find the z-score. So this data point of 200 is how many standard deviations away from this distribution. So we're gonna take the data point.
We're good at 10.
Yeah, very good. So let's calculate it. So we're gonna take the data point of 200 minus the mean of 180, and then divide by, so this ends up being 20 pounds away from the mean, but the standard deviation is 2, meaning that there are 2 pounds for each one standard deviation. So if we take 20 divided by 2, that gives us 10. So this tells us the z-score is 10, which means we're 10 standard deviations away from the mean. So that means we're very, very far right of the mean on this distribution. So now that we have 10, let's go ahead and find the left area. So using the table, what left area do you get by trying to find 10?
9.
Yeah, it turns out that 10 is so far to the right that the table doesn't even have it. The table maxes out at a z-score of 3.5. So if you look, if I redraw this picture to reflect that this data point is very far right, let's say z-score of 10 is here. It's not to scale, because if I had more board space, it would actually be all the way over here. So let's say it's here, but the z-score table maxes out at a z-score of 3.5, let's say that's here. Because at a z-score of 3.5, that's already covering almost 100% of the values, and covering the biggest possible value you could expect to observe already at 3.5. But we're at a z-score of 10, all the way over here. So out of z-score of 3.5, what left area does the table give you? Yeah, very good. 0.9999, which is 99.99%. So that's the total left area. And so what would the area to the right be? So what would the total area to the right? Yeah, it would be 0.0001. So if the z-score had been 3.5, then the right area would have been 0.0001. But our z-score is 10, so that means that the right area is less than or greater than that 0.0001. 0.0001. So we're looking for now this area to the right of a z-score of 10.
I don't think you can get any smaller.
Yeah, so this total area is only 0.0001, but we are only looking at a part of that area, so our area is now gonna be less than the 0.0001. So this number, whatever it is less than 0.0001. So if you were to rely on the table, this is the best conclusion that we can make, is that the answer ends up being a very small probability. It's less than 0.001. It ends up being a lot less than 0.001, because this z-score of 10 is so much further to the right than the z-score of 3.5. But for now, all I want you to get from this is that this probability ends up being very low. It's virtually zero. So that means that the probability that you gather a sample of 100 men and the average weight of the 100 men is greater than 200 pounds, it's virtually zero. Because if you want the average of 100 men to be more than 200 pounds, then all of the 100 men each have to weigh more than 200 pounds. And that's a large constraint that you're putting on each man. So this is virtually zero. And if we contrast that with the answer that we saw before, which is 15.87% of the time, one man weighs more than 200 pounds, then this is a big difference. So this is an example of the central limit theorem when you're asked to find the probability when a variable represents a sample mean. So if you have a variable that represents a sample mean, then we use the central limit theorem. That tells us that that variable will be distributed as a bell curve, and also it tells us that what the mean and what the standard deviation of that bell curve are. So we use the central limit theorem in this case. But keep in mind that we also talked about the assumptions of the central limit theorem. When it's true that this distribution of sample means will indeed be a bell curve, and we said that that's true if the sample size is at least 30. So in this example, the sample size was indeed 30, and that's why we were able to use the central limit. Any questions? Okay, so let's say that I now change this question to, I select a sample of 10 men now. But everything else is the same. The average weight of this 10 men is found, and then I want to find the probability that that sample mean weight of the 10 men is more than 200 pounds. So do you think I can continue with the approach that we did before, which is to use the central limit theorem to find the probability?
Yes,
Okay, so why yes?
because it either has to be greater than 30 or at 30 or the original distribution.
Okay, very good. So any one of these assumptions can be true. So this is an or, so either the first one or the second one. So either the sample size is large enough, or if it's not, then the original distribution of individual values, if it's already distributed as a bell curve, then you can use the central limit theorem. And it turns out that this original distribution of individual weights is already distributed as a bell curve. Okay, any questions? All right. So let's do another similar question here. So let's say that we go back to the 100 men. But after we select 100 men and we weigh them, let's say that instead of taking the average, you find the total. So you stop short of finding the average, you just find the total. And so instead of the sample mean weight being found, let's say that the total weight is found. And so, then our question is, what's the probability that that total weight is more than, let's say, 19,000 pounds. So now our variable doesn't represent a sample mean weight, it represents the total weight out of the 100 men. So we haven't talked about what the distribution of a sample total looks like. We've only talked about what the distribution of a sample mean looks like. So can we convert this situation into one that we actually know how to handle, which is, can we convert this variable, which represents a total, into a mean? Can we convert a sample total into a sample mean so that we can use the central limit there? Okay, so let's back up a little bit then. If I have a sample of 5 numbers. Yeah, good, good. So let's say we have a sample of 5 numbers, and we know that the total of that sample is 30, then can we find the mean? How do we find the mean?
Divide the total by the sample size.
Yeah, very good. So by definition, the mean or the average is simply the sum of all the numbers, or the total of all the numbers, divided by the number of numbers. So since you have the total given to you already, you just take that total and you divide by the number of numbers, and that'll give you the average or the mean, right? So the mean here is just 30 divided by 5, which is 6. So here you're asked to find the probability that this total is greater than this reference number. So can you convert this total to an average or mean? Yeah, so all you do is take this 19,000 and divide by the number of numbers, which is 100. And so the total weight divided by the number of numbers ends up being the sample mean. So now you've converted this total weight back into a sample mean. And if you divide the 19,000 on the right by 100, you'll get the sample mean that this total is supposed to be, and what's that? 190. So now this is the same question as what's the probability that the sample mean weight is greater than 190? And it's basically the same question as the one we did previously.
It's 19 actually.
Oh,
Oh wait,
one
no,
nine.
sorry,
It's
I
one
missed
nine.
the 0, I missed the 0, that's my bad.
okay, any other questions? Yeah, so basically, we started with the probability that the total weight of a sample was greater than this big number, 19,000. But then we said we could convert this variable that represents a total weight into one that we're more familiar with, that the central limit theorem addresses, which is a sample mean value. So we can convert a total sample value into a sample mean value by dividing this number that represents the total value by the number of numbers, which is 100. And so this problem now becomes the probability that the sample mean is greater than 190. And now we can use the central limit theorem for it. Okay, any questions? All right. So let's maybe do another example, just as practice. Make sure that we're on the same page. So let's say that we're dealing with the same type of variable. Let's say we're dealing with weight here. Weights of men. And let's say that the mean is 180, standard deviation is 20. And so, let's say that we have this elevator. And, let's say that the maximum number of people that it safely holds is, let's say, 10 people. And let's say that we also know that the maximum weight capacity of the elevator is 19,500 pounds. So the question is, if you have 10 people in an elevator, what's the probability the elevator is gonna fail? So, if 10 people in an elevator, what's the probability that the elevator fails? Okay, so let's talk about it. Okay, so this probability we're trying to find, the probability that the elevator fails, what does that mean in terms of the weights that the 10 people can be?
They have to add up to a number that exceeds the max weight.
Yeah, so basically, the total of the 10 people has to be greater than 19,500 pounds. So we want the probability that the total weight of 10 people is greater than or equal to 19,500 pounds. But again, this variable that represents a total weight in a sample of 10, a total in a sample of 10 people, that's not something that we really know the shape of. We haven't really formalized that. But we do know how to convert a total value of a sample into a mean value of a sample. So, how do we do that?
Divide by sample size.
Yeah, so we're gonna convert this total value of a sample of 10 people into a mean value by just dividing this total by the number of numbers in the sample. So we're gonna convert this total into a mean, weight in a sample of 10. And that has to be greater than or equal to the 19,500 divided by, yeah, let me use a smaller number. So let me use 1,950 for the maximum weight of the elevator, because otherwise it will never fit. Yeah, so let's say 1,950. So that was the total, and then we convert that total to a mean by dividing by the number of people, or 10. So this is the same question as asking, what's the probability that the mean weight in a sample of 10 is greater than or equal to 195 pounds. So it'll be more instructive if I change the first one to this. So these two are the same probability, really. And then the second probability, because we're dealing with the probability of a sample mean relative to a number, now we can use the central limit theorem directly. But we only have 10 people, a sample of 10. Can we still use the central limit theorem? Yes, because of this or condition on the assumptions is that the original distribution of weights is already normally distributed, so we can go ahead and use the central limit theorem. And moving forward then, central limit theorem says that the distribution of sample means, which is what we have as our variable here. So this is the sample mean weights in 10 people. It's normally distributed with now this mean and this new standard deviation. So what's the mean of this new bell curve? Yeah, it's the same as the original, 180. And the standard deviation by the central limit theorem is the standard deviation divided by the square root of n. So that'll be the 20 divided by the square root of 10. Alright, so we're trying to find the probability that this variable is greater than this number, so that's the same as finding the area to the right of this number under the bell curve. So what's the next step to finding this right area? Yeah, find the z-score for this reference number. So the z-score of this data point is the distance of this data point away from the mean of 180 measured in the number of standard deviations. So this will be 195 minus 180 divided by this new standard deviation, which is 20 divided by the square root of 10. So if you punch this in your calculator, you type in the full expression, make sure that you're dividing by the entire 20 over the square root of 10, so you can use parentheses to ensure that.
Around 2.37.
Okay, 2.37. And if we look that up in the table to get the left area, what do we get? Was it? 0.991. Okay, so if that's the left area, what's the right area?
0.009.
Okay, good. It's, we'll start from 1. And so this ends up being the right area, which is the same as the probability we're looking for, which is the probability that this variable is greater than or equal to that number. Okay, any questions? So in this case, there's a almost 1% chance that the elevator might fail. Okay, so in this example, the elevator failing means that the capacity is exactly equal to 1950. So that's why we included the equal sign if the total weight was actually equal to that number. But what if we didn't include the equal sign? How would the probability change? Yeah, it ends up being still the same, because this is a continuous distribution, and including this value means that including that exact one value. And it turns out that it doesn't make a difference in the probability. Okay, any questions? All right, so what we just did was an example of the central limit theorem. This was the example of the second time that we used bell curves in this class.